Alright, so in this section we're going to be talking about two different types of comparison tests. The first one is going to be very similar to the comparison test that we talked about with integrals. So here, we're going to have some series that we're trying to evaluate the convergence or divergence of. And it's going to be something that we can't use our general methods on. So what we're going to do is we're going to compare it with some series of some sequence b sub n. Right? Now the important thing to mention here is that both of these series have to have positive terms, and that even though I'm writing, we have some from n equals 1 to infinity, we don't have to start at n equals 1. And so here's what we can say. If the series with b sub n is convergent, and a sub n is less than or equal to b sub n for all n, so that means for each term in a sub n, the corresponding term in b sub n is going to be equal to it or bigger. If we have these two things, then that means that the series with a sub n is also going to be convergent. Basically, this just means if the larger series converges, then so does the smaller series. On the other hand, if the series with b sub n is divergent, and all of the terms in the series of a sub n are greater than or equal to the corresponding terms in the sequence of a sub n. All of those terms are greater than or equal to the terms in the sequence b sub n for all n. Then we know that the series with a sub n is also going to be divergent. Right? So basically this means that if the smaller series diverges, then so does the larger series. So let's start looking at some examples. Example 1 is a constant reminder to us that we should always use our test for divergence first. If we use our test for divergence, we'll get that the limit as this sequence goes to infinity is going to be 5. So we can say that this diverges by the test for divergence. Okay. Now let's actually get to a scenario where we use our comparison test. Here we can see that the test for divergence is going to fail. And this doesn't look like telescoping or geometric, right, or anything else that we can really... I definitely don't want to create the S sub n for this, right? So we don't really have anything else to use. So at this point we should be thinking comparison tests. So what we're going to do is we're going to call this sequence right here. This is going to be our a sub n. The first thing I note is that all of these things are positive, right? We're plugging in positive numbers on top and bottom, so our fraction has to be positive. Okay. And so now what I'm going to do is I want to kind of make this look like n to some exponent over n to some exponent, because then I can look at it as a p-series and know if it converges or diverges right away. So what I'm going to do is I'm going to look at the complicated part, which is the denominator. And I know that n to the 8th plus n squared plus 1 has to be greater than or equal to, right? I'm saying, well, you can always do greater than or equal to, and it's just a safe assumption. So I'm going to say that this is greater than or equal to just n to the 8th. Right, because I've removed this n squared, I've removed plus 1, so I'm removing positive things we're adding to n to the 8th. So this inequality must be true. Now what I'm going to do is I'm going to flip it and make it into a fraction. So this tells me that 1 over n to the 8th plus n squared plus 1 is less than or equal to, right, since I made it into a flat fraction, I have to flip my inequality sign. So this is going to be less than or equal to 1 over n to the 8th. Now, to make this left-hand side look like my a sub n, I'm going to multiply both sides by n to the 4th. Right, I'm multiplying by a positive thing on both sides, so I haven't changed my inequality. And now what I notice is that this n to the 4th over n to the 8th is the same thing as 1 over n squared. And I know that the sum from n equals 1 to infinity of 1 over n to the 4th, over n squared, this is my b sub n. This is going to converge by our p-series. So what I've gotten here is I've gotten something that's bigger, always bigger or equal to, and it converges. So that tells me that the original series must also converge. So we say that this series converges by the comparison theorem. And we'll denote that as CT. This is not a CAT scan, this is the comparison theorem. We don't use CAT scans to determine whether something converges or diverges. Or well, at least we don't use them to determine the convergence or divergence of series. Okay. So now I'm going to look at this part. So the first thing I notice is n equals 3. So I'm looking at that denominator because I see a negative sign, which means, okay, maybe we get a negative in the square root, which would be bad. But 3 to the 5th minus 3 is certainly going to be positive. And it'll stay positive for all the times I plug in bigger n. Okay, so this is going to be positive, and this will be our a sub n. So again, what I look at is the complicated part, which is the denominator. And so I can say that, well, and we should also use our test for divergence, right? We know that the test for divergence is going to fail here because we'll have a highest degree of 2 on top and a highest degree of 2.5 on bottom. Right, so that'll fail. And what I'm going to note is that the square root of n to the 5th minus n is always going to be less than the square root of n to the 5th. Right, and this is the same thing as saying n to the 5/2. So what does this tell me? This tells me that 1 over the square root of n to the 5th minus n is going to be greater than 1 over n to the 5/2. Now I'll multiply by n squared plus 1 on both sides. And in order to make this right-hand side look like a p-series, what I want to do is get rid of that plus 1. If I get rid of the plus 1, then this is just going to get smaller. So we'll have n squared over n to the 5th, or n to the 5/2, right? And so this is going to be equal to 1 over n to the 1/2. Because what I'm doing is just subtracting exponents there. And so now this tells, so I can look at that sum. Well, that sum is going to diverge by the p-series. Which means, since we got something that is always smaller, and it diverges, that means our bigger thing has to diverge. So that tells me that the sum from n equals 3 to infinity, I'm just going to write a sub n, right? That's that sequence given, is going to diverge by the comparison theorem. Right, and so a lot of times as answer choices on quizzes, homeworks, tests, we'll say, okay, this converges by the comparison theorem with, and then some series. That's generally how you'll see that phrased. Okay, let's look at example 4. This one's a little bit more complicated. So I'm going to look, it's safe to say that both the top and the bottom are complicated. The first thing I'm going to do is kind of simplify the bottom. So I can rewrite the bottom as n to the 7/2, right? Because I'm just adding exponents right there. Now what I know that the sine function is between -1 and 1. So -1 plus 5 will give me 4. So that means that 4 is less than or equal to sine of n plus 5. Which is less than or equal to, so the upper bound for sine of n is 1, so 1 plus 5 will give us 6. Which tells me that, so what I'm looking at is we're going to have a denominator of n to the 7/2. If I'm thinking about this series with 1 over n to the 7/2, I know that's going to converge since it's a p-series. So I want to look at the bigger inequality, meaning I want to look at the fact that sine of n plus 5 over n to the 7 halves is less than or equal to 6 over n to the 7 halves. Now the way we make this into a p-series, since we just have a constant being multiplied on top, we can actually pull this constant out of our series. So this is going to be the same thing as 6 times the sum from n equals 1 to infinity of 1 over n to the 7 halves, which is going to converge since it's a p-series. Alright, and so since I have a bigger thing that converges, we can say that the smaller thing, so this is our a sub n, we can say that the sum from n equals 1 to infinity of sine of n, I'm just going to write this as a sub n. We can say that this converges by the comparison theorem. Now example 5 looks almost exactly the same except for that denominator looks different. So here we would look at, again, we know that 5 plus sine of n, and so I haven't been checking this, but I created these problems so I know they fail the test for divergence. But you should go through and check test for divergence on these, if anything, just to make sure that you're up to date on calculating limits and stuff. So this is still within the same bounds. Now on the bottom I'll have 1 over n to the 1/2. I know that's going to diverge by p-series. So what I'm going to do is I'm going to focus on the smaller inequality. So I'll look at 4 over n to the 1/2 being less than or equal to 5 plus sine of n over n to the 1/2. Well, again, we can rewrite that part on the left, so we're going to have 4 times the sum from n equals 1 to infinity of 1 over n to the 1/2, and we know that this is going to diverge by our p-series test, which tells me that our original series must also diverge. And this is going to diverge again by the comparison test. And so for example 6, this is a much more complicated one. And the only reason it appears so complicated is because we generally don't remember a lot about arctan. What we need to remember about our arctan function is that it repeats over and over again, but if we're going to actually make it a function, we bound it between negative pi over 2 and pi over 2, and it looks something like this. Right? So, in particular, arctan of n is going to be bounded between negative pi over 2 and pi over 2. So I can say that 5 minus pi over 2 is less than or equal to 5 plus arctan of n, which is less than or equal to 5 plus pi over 2. Okay, well, 5 plus pi over 2, that's like 3.14 over 2. What I'm going to do is I'm going to make that even bigger. So instead of pi over 2, I'll call it 4 over 2. So I'm going to say that this is less than or equal to 7. Now the reason I'm choosing to focus on the big one, the bigger inequality, is because we're going to have 1 over n to the 4th, or some constant over n to the 4th. And so I know that's going to converge by p-series. So I'll divide this by n to the 4th. We can say that the sum from n equals 1 to infinity of 7 over n to the 4th, we can pull out the 7, and then we can say that this series converges by our p-series test. Since I have something that's bigger and it converges, that's going to tell me that our original series must also converge. All right. So now let's look at some more complicated cases. So here we have 3 over 5n plus n. All right. So I'll look at the more complicated part, which is the 5n plus n. If I have 5n plus n, if I take away this positive n, then we have to get smaller. So this is going to be greater than 5 to the n, which means that 1 over 5 to the n plus n, is going to be less than 1 over 5 to the n. I'll multiply by 3 on both sides. And now we should recognize this right-hand side as a geometric series. So we want to see if it converges. Well, so we'll have the sum from n equals 1 to infinity of 3 over 5 to the n. We know that we need to rewrite this as a times r to the n minus 1. So this will be the sum from n equals 1 to infinity of 3 over 5 times 1 over 5 to the n minus 1. Here's our r value. It's less than 1. So we know that this is going to converge. Right? And so this is a convergent geometric series. Which means, so since we got something bigger that converges, then our original series must also converge. Right, so this means that this must also converge by the comparison test. All right, now we come to example 8, which is going to make us look at a different comparison test, but let's see why it makes us look at a different comparison test. So I rewrite this as n to the 3 halves, sum n equals 5 to infinity, n to the 3 halves over 8n squared plus 6n. And so I'm going to look at the more complicated part, which is the bottom. So we have 8n squared plus 6n. Well, this is greater than 8n squared. So then we get that 1 over 8n squared plus 6n is less than 1 over 8n squared. I'll multiply by n to the 3 halves on both sides. And so this is going to be 1 over 8n to the 1/2. And so our issue here is that this b sub n we've created, right, when we look at this, we'll have 1 over 8n to the 1/2. So this is 1/8 times the sum from n equals 1 to infinity of 1 over n to the 1/2. And this, what's a good color? I like this one. This diverges by our p series. Okay. What this means is that our comparison theorem may not work because we got something that's bigger, but it diverges, right? For the comparison test to work here, we needed this to be smaller and diverge. All right, so what we say is that the comparison test may not work. The reason I say may not work is because it may be possible for us to get some nasty inequality over here, where stuff will cancel out correctly, and then maybe it works, okay? But instead of going in that direction, it's better for us to use something called the limit comparison test. So whenever the comparison test is inconclusive, right, whenever we say it may not work, that's when we apply this limit comparison test. And so what it does is it determines how whether the two series behave similarly for very large values of n. So again, we're going to suppose that both of these are series of positive terms. Okay, now if you take the limit of, as n goes to infinity, of the a sub n sequence over the b sub n sequence, and you get some constant number c where c is greater than 0, I don't know why I said c is greater than 0 and positive. They're the same thing. Then either both of these series are going to converge or both of them are going to diverge. All right? Note that if the limit is infinite or equal to 0 or negative for some reason, then our test is going to fail and we need to use some different kind of test or rearrange things differently. Okay. So to restate, if the limit as n goes to infinity of a sub n over b sub n is equal to c, where c is greater than 0 and finite, right, meaning that it's not infinite, then what we can say is then if a sub n, what I'm writing here is I'm saying that a sub n is similar, or sorry, basically equal to c times b sub n. This symbol right here, we call it approximately to, approximately equal to, right? So we say like pi is approximately equal to 3.14, okay? So if this is true for large values of n, then we get one of two things. If the sum, the series with b sub n, if this converges, then that tells us that multiplying by constant, right, some finite constant, this is still going to converge. Which means that the sum a sub n will also have to converge, right? Because these are approximately equal to the same thing. So they converge maybe approximately equal to the same thing. Similarly, if the series with b sub n diverges, then multiplying by some finite positive constant isn't going to change that, right? It'll still diverge. Which means that the sum with a sub n also has to diverge, since it's approximately the same thing for large values of n. Alright. Let's look at how to use this. Example 9. So we saw this one before. This is where our limit, this is where our comparison test did not work. What we had is that this will be our a sub n. Right, so a sub n is going to be n to the 3 halves over 8n squared plus 6n. And our b sub n, the thing we were comparing with, that was 1 over 8n to the 1 half. So now what I'm going to do here is calculate the limit as n goes to infinity of a sub n over b sub n. So it's going to be n to the 3 halves over 8n squared plus 6n divided by 1 over 8n to the 1 half. Well, that'll be the same thing as the limit as n goes to infinity of, let's see, this would be n to the 4 halves, which is n squared, over 8n squared plus 6n. And then L'Hopital's rule, sorry, this should be 8n squared up here. L'Hopital's rule would give us that this is equal to 1. This is greater than 0 and finite, so that tells me that by the limit comparison test, both will diverge since our b sub n series diverges. Alright, example 10. Looking at example 10, this will be our a sub n. And so we know that this is going to be less than or equal to. Alright, what I'm going to do is I'm going to get rid of the negative n cubed plus 1 on top. Right? Because notice if I'm plugging in 1, then that would be minus 1 plus 1. So I'm getting rid of nothing. Now if it's 2, if it's n equals 2, then that's minus 8 plus 1. So I'm getting rid of a negative 7, which means I'm making the numerator bigger. So I am making this fraction bigger. Now one way to think about this denominator down here is that as n gets extremely big, this negative n to the 6 plus 3 is no longer going to matter. Right, meaning that our dominating term is going to be the square root n to the 10th. Right, so this will be square root n to the 10th. This is the same thing as n to the 4th over n to the 5th. Alright, now this is going to be the same thing as 1 over n. We know that this is a p-series which diverges. Okay, so this is going to be our sum. This is going to be our b sub n, which diverges. So now I'm going to look at the limit of a sub n over b sub n. So we write limit comparison test. We'll do limit as n goes to infinity of, so let's see, a sub n, so we'll have n to the 4th minus n cubed plus 1 over square root n to the 10th minus n to the 6th plus 3 over 1 over n, which gives me the limit as n goes to infinity of n to the 5th minus n to the 4th plus 1 over square root n to the 10th minus n to the 6th plus 3. So again, going back to 152, one way to look at these limits as n goes to infinities when we have polynomials or even square roots of polynomials is to look at our dominating term, right, our highest degree. Right, so this is going to be limit as n goes to infinity. On top, we have n to the 5th dominating. On bottom, we'll have n to the 10th. And so the square root of n to the 10th will give us n to the 5th. So this is 1, which is greater than 0. Which tells me that both series diverge since the b sub n series diverges. Right? So we did our comparison, then we did our limit comparison test. We got a number that was finite and greater than 0, so we can say that they both have the same convergence or divergence, right? Not necessarily that they're both converging to the same thing, right? But we can just say that one converges and the other one has to converge. Since our b sub n diverges, they both have to diverge. Now let's look at example 11. Alright, for example 11, the first thing I'm going to start looking at is going to be the denominator. So, in the denominator, I'm going to get rid of that plus 2n, and I'm also going to change the inside of the parentheses. So I'm going to change this to less than or equal to 2n cubed. So notice that by removing that plus 2n and by removing that plus 1, I'm making this denominator smaller, which means that the fraction itself has to be getting bigger. Then on top, I'm going to change that from n plus 5 to n. Now, I know you're saying, okay, well, shouldn't this make our fraction smaller because we made the numerator smaller? Okay, yes, for like very small values of n, right? And even in general, it makes it smaller. But as n gets excessively large, that plus 5 isn't going to matter to us anymore. Okay, and I should have said, so this is going to be our b sub n. All right. So that gives me n over 8n cubed, which will give us 1 over 8n squared. All right, and so what I know is that this sum has to converge by the p-series. So now I'll look at our limit comparison test. So we have the limit as n goes to infinity of, let's see, we'll have n plus 5 over 2n plus 1 cubed plus 2n over 1 over 8n squared. So that'll give me the limit as n goes to infinity of, let's see, we should have 8n cubed plus 40n over, so it'll be 2n plus 1 cubed plus 2n. Alright, and so now if I look at dominating terms, we'll have this 2n, which gets cubed on the bottom, so that'll give us an 8n cubed. So we have 8n cubed over 8n cubed, which is going to give us 1, which again is less than or greater than 0, infinite. Which means that both series have to converge since our b sub n series converges. Alright, now let's look at example 12. Example 12 is by far the hardest problem on this entire section of notes. That's because there's not really an inequality for us to do. However, let's look at a graph real quick. So here I'm going to make the graph of sine. I'm going to try to do this carefully. That way my picture actually supports the nonsense that's going to spew out of my mouth. Okay. There is... I'm going to try this one more time. Alright. There's our sine of n function. Right, I'm not looking at sine of 1 over n squared. Actually, I'm going to call this sine of x. Now let's look at just the function y equals x. Right, so this was y equals sine of x. Oh my gosh, that always happens. You know how they say, like, you can fat finger a text message and, like, type the wrong thing? I think I'm, like, fat arming it, because my arm keeps on hitting the mouse pad. Alright, and so then here's my function, y equals x. And so what I want to notice is that if we take some circle like this, notice that sine of x might as well just be equal to x when x is near 0, right? Look at how incredibly close those are. If you don't believe me, plot it out on Desmos or something and just look at how incredibly close they are. So what we're going to say is that sine of 1 over n squared, it must also be near 1 over n squared for large values of n. The reason I say for large values of n is because this 1 over n squared is going to be going to 0 as n gets excessively big, which means that this is going to be approximately sine of 0, and so then we know it's going to be close to that 1 over n squared function. Okay, so our b sub n will be 1 over n squared. Alright, well that means that the limit as n goes to infinity of, so a sub n over b sub n, so sine of 1 over n squared over 1 over n squared. What I'm going to do here is use L'Hopital's rule. This will give me, let's see, on top we'll have cosine 1 over n squared times, let's see, the derivative of the inside, that should give us negative 2 over n cubed, and then divided by, so we should also have negative 2 over n cubed. And so this is going to be, right, we should get a cancellation here. And this should be the limit as n goes to infinity of cosine of 1 over n squared, which will be equal to cosine of 0, which gives us 1, right, which is greater than 0. And so then we can say both converge since the sum of b sub n converges, right? That was our 1 over n squared. All right, and that will conclude this section, right? So notice the main things here are knowing what these two tests say, right? What we need to use in order to use these two tests, as well as just being comfortable with, 1, calculating limits, and then 2, choosing these comparisons and the inequalities, right? Hopefully we've gotten a little bit better at this since we've already done the comparison test, or the comparison theorem for integrals.